Okay, grade 11s, welcome to my first Chalk and Talk in 6 months. I've actually missed this very much. I wish I was in a room full of people at the moment because it's lonely talking to a camera. Today I'm going to give you one of the first lessons of the grade 11 class, and I'm going to talk to you about numbers, and not just any numbers, but the kind of numbers that the computer understands. You may have heard the term digital. Yeah, in fact, I'm sure you have. Anytime we refer to anything that is digital, we are referring to something that is made up of numbers. And a computer is a relatively simple machine, and all it really does is arithmetic. It adds, subtracts, multiplies, and divides, and it does it so quickly that it looks like magic. So when you play a video game, all of the positions of the objects on the screen, and in fact the objects on the screen themselves, as far as the computer is concerned, they're just made up of numbers. And what it does is arithmetic so quickly that, it's seamless and it looks like magic. We need to learn about the numbers that the computer can understand. Now, numbers are numbers, right? You don't change the quantity by referring to it in a different way. So if there are 9 apples, it doesn't matter how I refer to it, the quantity of apples, 9, does not change. But the computer doesn't count like humans. Human beings, and you may never have thought about this, but we count in tens. And if you look at our numbering system chart, so 1, 10, 100, 1000, and I know you did this like in grade 2. If I take a number, let's say 498, put it in my place value chart, that's what this is called, 498. What I'm really saying is it's 4 times 100 plus 9 times 10 plus 1 times 8, and that's 498. That is the place value chart that we as humans use. And it's based on tens. You know, 1 times 10 is 10, 10 times 10 is 100, 100 times 10 is 1,000. The reason for this is really simple. We have 10 fingers, and the first thing that a young human learns to count on are their fingers. So we count in base 10, but the computer does not have 10 fingers. In fact, the computer has only 1 finger. The computer is a boatload of switches, all sandwiched down onto that integrated circuit that we talked about yesterday. The switches are called transistors, and they can only register 2 states. The presence of electricity and the absence of electricity. That simplifies it a lot, but the computer can only see 2 values. So when we devised the computer, we had to find a way that the computer could count or do math when it could only recognize 2 values. So we needed a number system that had only 2 digits. Enter binary. Now, if we look back at the etymology of the word binary, which is a fancy $10 word that I don't use very often, bi means 2, and nary means number. So the binary number system is a number system that is made up of simply 2 numbers, 1 and 0. You may have noticed that on some of your appliances you will see this written on the off-on switch. And that simply describes the operation of the switch in the binary number system, where 1 is on and 0 is off. Bet you never thought of that before. Maybe you did. I don't know. So, how can a number be reflected in the binary number system? A binary number is a number that's just made up of 1s and 0s, and it might look like that. 1, 0, 1. Now, when I look at that number, I see 101. How do I know that that's not 101? I don't, unless you put a little subscript 2 after it. That little 2 just means that this 101 number is in the binary number system or the base 2 number system. And so I know then that that's not 101, that's a binary value that I need to decode. How to decode a binary value? Really simple. Converting a binary number, which is a digit base 2 number, to a base 10 number is really easy. All I need is the place value chart that the computer uses. So I need one in binary. Easy. 1, 2, 4, 8, 16, 32, 64, 128, 256, 512. And where does it go? Well, it goes on to infinity. Any number that you can reflect in the decimal number system in base 10, you can reflect in binary. If I have this place value chart, I take my binary number, which is 101, right? The 101 base 2. I put it in the chart in exactly the order it appears. So the number at the furthest right has to go in the column at the furthest right in my binary place value chart. So I think you guys can see how that is. So now all I have to do is multiply and add. 1 times 4 is 4, 0 times 2 is 0, and 1 times 1 is 1. Add it up, my number is 5. So 101 in base 2 equals 5 in base 10. Easy peasy. Let's do another one. So I'm going to choose my favorite binary number. Let's pick one that is, I don't know, several digits long. By the way, every number in binary, every individual 0 or 1, is referred to as a bit, which is short form for binary digit. So let's make up a 6-bit number. 1, 1, 0, 1, 1, 1. Put our little subscript 2, which indicates that it's binary. Put it in the place value chart. Now I just have to multiply and add. So I get 32, 16, and 4, and 2, and 1. Add them together, so 6, 7, 8, 12, 14, 15, 16, 3, 4, 5. So 110, 111 in base 2 is 56 in base 10. Now, little secret, when you're dealing with computers, these numbers, they're magic. You'll see them come up time and time again when you're dealing with computer hardware, with computer software, anything to do with computers. If you go out to buy computer memory, you can buy it in 2 gigabytes, 4 gigabytes, 8 gigabytes, 16 gigabytes, and so on. You never see 11 gigabytes of RAM for sale because it's not in the binary place value chart and it's not a magic number. All right, so hopefully you've got that. You can look at this again. There's a handout in the hub folder for you that shows you how to do this in print. If you're having troubles, email me, hit me up on the chat. I'll help you with that conversion. Now I want to show you how to convert the other way, which is taking a decimal number and converting it to binary. This is a little more complicated, but it's not like super rocket science. So I'm going to show you, and I refer to a game called The Price is Right when I play this. You guys may never have seen The Price is Right. It's a television game show. It still runs, it airs every day at noon. I don't think you need to watch it. But basically the key to The Price is Right is that you have to guess how much something costs as close as you can without going over. So that's the game we have to play here in order to take a decimal number and convert it to binary. So let's take a decimal number. Any old one, let's say 11. Okay, so I have 11 in base 10 and I want to convert it to binary. It's just a series of steps you follow over and over again. That's called an algorithm. Follow these steps over and over and you will get the answer every time, no matter how long the number is. If you need more places in your binary place value chart, you need more than 512, just go ahead and make them. Binary place value chart is really easy to make. Every column is simply the column before it doubled. So 1 times 2 is 2, 2 times 2 is 4, times 2 is 8, times 2 is 16, right? So you could make a binary place value chart as large as you need it. All right, so 11. Find the number in the binary place value chart that is as close as possible to 11 without going over. Simple. That's 8. Place a 1 under it and subtract it from the number that you're trying to convert. So 11 minus 8 is 3. Play again with this number. Closest possible to 3 without going over, that'd be 2. Place a 1 under it, subtract it, I'm left with 1. As close as possible to 1 without going over, well obviously that's 1. Subtract 1, you get 0. Okay, when you reach 0, ding, 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 you won. Once you've won, take any blank that you don't have in the place value chart, anywhere there's no value, place a 0, and there's your answer. 1, 0, 1, 1 in base 2 is 11 in binary. If I want to check my answer, I can just convert back. So 1 times 8 plus 1 times 2 plus 1 times 1. So that's 8 plus 2 plus 1, which is 11. So I'm correct. All right, let's do one more example. See what we got here. Let's pick a little bit larger number, like I don't know, 130. Now that sounds like it's going to be really intimidating. It's not always more work calculating a larger number. It's just kind of random how it fits in the table. So 130 in base 10 in binary is what? Well, let's find out. Number in the chart closest possible to 130 without going over? That's 128. Place a 1. Subtract 128. I'm left with the value of 2. Number in the binary place value chart, as close to 2 as I can get without going over? Well, that'd be 2. 2 minus 2 is 0. So, I'm done. I won. All I gotta do is put zeros. So 1, 0, 0, 0, 0, 0, 1, 0. In base 2 equals 130 in base 10. There you go. Conversions between binary and decimal and binary simplified. There's a binary practice sheet for you in the hub. Please give that a go, give those numbers, calculate them, and we will take them up. I'm back.